Hello, this is Mr. White, and this video is on infinite geometric series. And if you're intrigued by the animation you see on the screen right now, I'd encourage you to let your eye follow any one of those ants for a little while, and you'll understand why this is an example of something called a one-sided surface. In particular, this one-sided surface is called a Mobius strip, and this animation is based on a woodcut from the famous Dutch artist M.C. Escher. And I'd encourage you to Google either Escher or the Mobius strip, up your math cred a little bit. Now, this animation is not directly related to the lesson, but I chose it because number one, it's interesting, and number two, its shape resembles the infinity symbol, which is the topic for today, infinite geometric series. All right, when we first introduced series, I showed you this infinite geometric series. We know it's infinite because the dot, dot, dot says so. We know it's geometric because every time you go from one term to the next, you are multiplying by the common ratio of 1/2. So it's an infinite geometric, and since we're adding them up, it's a series. Now let me introduce this notion of partial sums. I don't think I mentioned that before, but it's not a hard one. Partial sums are sort of an attempt to get your head around infinite geometric series. Even if from the previous class example you know what all these terms add up to, let's pretend that you don't. And let's say we're just trying to get a handle on this thing. We might start by just adding up the first one term and saying, okay, the first partial sum is 100 if I add up the first one term. Now, if you're not seeing where I'm going with this, just hang on. I think you'll get it here shortly enough. If I say, what happens if I add up the first two terms, a sub 1 plus a sub 2, that would give me my second partial sum, s sub 2, which is 150. If I add up a sub 1 plus a sub 2 plus a sub 3, my third partial sum is 175. And so if you have an infinitely many terms, you might start by just saying, I'm going to add up the first 3, 4, 5 terms and see if I can detect a pattern, see if I can get a sense of what's going on. And when we discussed this in class, we pretty quickly concluded that we get the sense that those partial sums are not going to just explode to infinity, as I could do s sub 100, s sub 1,000. We get a sense that it's not going to explode to infinity, but that it will approach or converge to some finite value. And we speculated that as we go to the infinite sum, that s sub infinity might equal 200. Now, typically, we won't write the subscript infinity. Typically, if you just write s, that's implied to be the actual total infinite sum. And again, we speculated that that would be 200 in this case. Well, we further backed that up with a nice sort of pictorial piece of evidence here where we said, okay, now it's pretty compelling to believe that if you take a square, a 10 by 10 square with area 100 square units, and you put right next to it this rectangle that's half as big, a 50 square units, and then a 25 unit square, and then a 12.5 unit rectangle, we could pretty quickly and convincingly see that no matter how many terms I add up, that total area is really just 200. Okay, now our goal for this lesson is to say, okay, well, that was pretty convenient for this series, but what about in general? What about for any converging infinite geometric series? Well, let's dive right in. Let's say this is our series this time, and it's harder. In fact, I can't really think of how to come up with a nice sort of geometric interpretation of this one. It's a little more difficult. Probably could, but I think our time is better spent just tackling this algebraically. Let's first of all remind ourselves that you always have to look at the lower bound. That tells you where to start your series. That says that I'm going to start with a sub 1, and that the first value I'll plug in for I is 1, and then followed by 2 and 3 and so on. Okay, so when I take that first lower bound and I plug it into the exponent, I see it's our familiar form of a times r to the I minus 1. That's a pretty familiar form for geometric series by now. And if I plug a 1 up in there, I get 2 times negative 9/10 to the 0 power, or just 2. Notice that when you plug in a 2 for the second term, 2 times negative 9/10, that will give me negative 9/5. So I could think of this as 2 minus 9/5. Sometimes I prefer just to write this out the long way, just so I could see the pattern a little more clearly. And the third one, the third term, 2 times negative 9/10 squared, and so on. All right, and again, our question is, what do all those really add up to? You may have a hunch, you may not. You may have a hunch that this approaches a finite sum, and I'll go ahead and tell you for now that it does. We'll delve into later, probably in class, how do we convince ourselves that that's true. But let's say that equals, if I were to add all those up, it would equal some number s, and we want to find out what s is. Well, we're going to use an approach that should feel kind of familiar by now. I'm going to multiply that s by what? The common ratio. So if I multiply s times negative 9/10, this first term would get 2 times negative 9/10. Now, I wrote it over to the right a little bit, but remember, it's this first 2 that I multiplied by negative 9/10 to give me that term. And if I take this second term and multiply it times negative 9/10, that would give me 2 negative 9/10 squared, and so on. Again, I'm trusting this feels kind of familiar. All right, and then our next trick was to say, what if I take the first row, the green row, and subtract the black row? What if I take s and subtract this? And that would give me s minus negative 9/10 s. And on the right-hand side of the equation, this is the wonderful part where all these terms cancel out, and I'd get just 2. All right, I'm going to do something a little strange here. I'm not going to simplify the left side. Instead, I'm going to factor out the s. And I'm going to say on the inside I have 1 minus negative 9/10. And then I'll go ahead and divide over that, what I need to get s by itself. And now I'll simplify. There's a reason for that. We'll find out shortly. That's 2 over 19/10. That's the same as 2 times 10/19. That's 20 over 19. All right, and I'd encourage you, if you have Excel or Google Spreadsheet or whatever spreadsheet program, I'd encourage you to play around with confirming that. Remember, we'll go into, we'll say our first term was 2. I'll type in the recursive formula on the cell below it and say that it equals the previous cell times negative 9/10. And in this cell to the right, let me make that yellow. I'll remind you that there's probably a sigma button somewhere, and I'm going to use that and say, let's make this the sum of that entire column. And right now, the second partial sum, since I only have 2 terms in there, this gives me the second partial sum, which is 0.2. The third partial sum adds a positive term, so the partial sum climbs back up to 1.82. But as I add the next negative term, it goes back down to 0.362. So we see that in this case, this is something called an alternating series, where these terms flip-flop between positive and negative, and that sum just keeps bouncing up and down. But it bounces up and down by smaller amounts. And as I continue to look at more and more partial sums, in fact, if I just scroll down, let's do the 100th partial sum, I see that it's now kind of leveling off to 1.0526. Even if I go down to the 200th partial sum, by now it's not going to change a tremendous amount. So it's currently 1.0526. If I had another 100 terms, it didn't change a whole lot. So let's compare that to what we got algebraically in the cell right beside it. I'm going to say, hey, Excel, what's 20 divided by 19, which was our answer? And we see that it confirms what Excel had told us, 1.052632. All right, now this is what I call doing it the long way, finding the infinite sum the long way. And again, I really think there's a lot of value in doing it the long way, taking 2 minutes to do it the long way, whereas we're going to find that there actually is a short way, which takes a little less time but offers less insight. I'd encourage you to mix it up, do it both ways. And I'll acknowledge that for infinite geometric series that converge, it's awfully tempting to just use the formula because it's a fairly simple one. let's find out what it is. Now I'm going to ask you to just take on faith for right now that the infinite geometric series will converge if and only if the common ratio is less than 1. And on some level, I hope that's intuitive. We'll certainly discuss it more in class if, as needed. But I actually need to amend that a little bit. It's really when the absolute value of the common ratio is less than 1. That's when we're going to say that the series converges. And we see that, we kind of get some insight into that when we look at this formula for finite geometric series. If I say that, okay, this is no longer just some finite number n up here, this is actually infinity, that means that this n essentially becomes an infinity. And we get the sense that if absolute value of r is less than 1, we should get the sense that this term is going to get smaller and smaller and smaller. Imagine that r was 1/2, let's say. And if you raise 1/2 to the 10th power, 1/2 times 1/2 times 1/2 10 times, it's getting smaller and smaller each time you multiply by a half. And then as you say, I'm going to multiply it times itself 100 times, it gets really, really tiny, almost negligible. And if we go ahead and say, you know what, let's pretend that n is just an infinity, let's pretend that infinity is a number and I can plug it in up there, we're essentially going to say that that is just 0. Notice that would not have happened if we did not have this condition. So if r was equal to 2, and you raise it to the 10th, the 100th, the 1000th, the infinity power, it does not get smaller and become negligible. It explodes to infinity. So that offers a little insight as to why this condition is required for a series to converge. So if that condition is met, I hope you're convinced, and again, we can certainly discuss more, well, I hope you're convinced that that term will pretty much go away, and we'll be left with this simple formula. And let's take a look at that last example and see that I basically had this particular formula at one time. A sub 1 over 1 minus r. If I go back to the previous slide and scroll down, that's why I wrote the series this way, or that's why I wrote my final line this way. That's our a sub 1, and down there I have 1 minus r, which was negative in this case. So I want to show you that happens every time, no matter what your a and your r value are, you end up with that format every time. And therefore, you get a quite simple formula that is awfully tempting to use. And again, I recommend that you do it the long way to remind yourself where that formula came about, but you also, maybe the other half of the time, do it the short way, which is using this formula. So let's, here it is formally stated that the sum of an infinite geometric series converges if and only if the absolute value of the ratio, the common ratio, is less than 1. And if it does converge, the sum is a sub 1 over 1 minus r. Now, there's one little nuance that you need to be aware of. That formula holds if you have a k equals 1 down here. However, what happens if you had like k equals 0 or something like that? Actually, let me just drag this onto the screen. What if we had something that fit this format instead? Well, then it would be a sub 0 over 1 minus r. Here's kind of the bottom line. This numerator is going to be the first term in your series, whether it's a sub 1, a sub 0, or something else. So let's do an example that shows that we just have the first term in the series in the numerator. All right, whoops, let me skip that. Here we go. So I'll still suggest that rather than jump straight to the formula, here we're finding a summation where you've got k equals 0 here. And notice that the exponent's a little different than usual too. I'd still suggest that before you jump to the formula, write out the first few terms. A sub 0 is going to be 5 times 3/4. And if I plug 0 plus 2 in there, I just get a 2 in my exponent. And then a sub 1 would be 5 times 3/4 to the third, and so on. But again, I emphasize that when you use that formula, you just take the first term. So let's go ahead and say that that sum of all the infinitely many terms, in this case, is going to be the a sub 0 term, the first term, over 1 minus r. That doesn't change. And r in this case is 3/4. So 5 times 3/4 squared, that's the same as 3 squared over 4 squared. And on the bottom here, I have 1/4. And dividing by 1/4 is the same as multiplying by 4 over 1. That means that this 4 cancels out one of these 4's down here, and I get 5 times 3 squared, which is 45 over 4, and that is my sum. If you prefer to make that a decimal, that would be 11.25. So whether you call it 45/4 or 11.25, I don't really care. Let's go to Excel and just see if that makes sense. So I go up here, and real quickly I'll say, let's see, 5 times, now remember the first term was 5 times 3/4 squared. And if each successive term, I'll enter that recursive formula, say it's the previous one times 3/4. And I'll just go ahead and jump to the conclusion here. I'll add a whole bunch of terms. And Excel confirms that, yeah, it's pretty much 11.25. All right, here's some for you to try. Again, I'd suggest you do 1 or 2 of them the long way, and then the other 2, just use the formula. Get comfortable with both ways. Okay, trusting you paused the video and tried it out. Let's see how you did. There are my solutions for the first 2. Here are my solutions for the second 2. I just tended to use the formula here, but again, doing it the long way would have yielded the same results. All right, of course, come on by if you have any questions.